So thank you very much. So yeah, yesterday I couldn't really finish, so I'll pick up there today. So I presented some key results from large deviations theory, and today I want to start with some general concepts that allow you to deduce large deviation principles from existing ones. So the first principle, so I'll not say a lot because the idea of today's lecture is somehow I picked an example related to LPN balls, in which you can see all these principles that I present now and yesterday's theorems in action. Yeah? So I'll just present them, and then you'll see them applied in a few moments. Okay. So the first principle that I'm going to present is the following. So you have random variables, or a sequence of random variables that satisfy an LDP at a certain speed Sn and with a good rate function Ix, and you have another sequence satisfying at the same speed an LDP with a good rate function Iy. Then if these two if the random variables are independent, okay, then you know that the vector containing the coordinates xi and yi, that this sequence of vectors satisfies an LDP at the same speed as n, and the good rate function is just the sum of the rate functions. Yeah. So this is the first principle. So if you have a vector like this and the coordinates are independent and they satisfy LDPs at the same speed, then you get an LDP for the vector, and the rate function looks like this. Okay. So the next principle, which is known as the contraction principle, is as follows. So let's say we have two Polish spaces and we have a continuous mapping between these two Polish spaces. Then if mu n is a sequence of probability measures on your Polish space E1, satisfying an LDP at a certain speed Sn with a good rate function, then you can somehow transform this measure. You look at the push forward. Yeah? So you look at the push forward here, which is mu n after f, or f to the minus 1. And this push forward then also satisfies an LDP on the space E2 now with the same speed. And the good rate function that you get on E2 is as follows. It's j of y is equal to the infimum over all x in E1, yeah, such that f maps x onto y. Yeah? Then you take I of x. Yeah? So you can transform the LDP from one space to the other, okay, via a continuous mapping. Yeah? So this is known as the contraction principle. And the third principle essentially says that if you have two sequences of random variables and they're very close on an exponential scale, then they satisfy the same large deviation principle. So more precisely, if again, or let's say we have a metric space and two sequences of random variables taking values in E, and assume that your sequence xi satisfies an LDP at a certain speed Sn with a rate function Ix. Then if the sequence y is close to x on an exponential scale, so they are exponentially equivalent, which means that the lim sup of 1 over Sn log of the distance of the two is larger than delta is equal to minus infinity, yeah, so they're somehow exponentially close, then the random variables yi, or the sequence, satisfies the same large deviation principle. Okay, so if they're close on an exponential scale, you have the same LDP. Yeah, so these are three principles, and now I want to talk about some large deviation results related to LPN balls. And as I said, this is a rather elementary example, that I chose, but you will see essentially all the results that I've presented in action now. Yeah. So until very recently, most of the large deviation results that were obtained were related to LPN balls. Okay, and the reason, I already mentioned this yesterday, is that we have a probabilistic representation due to Shechtman and Zinn, which allows us to rewrite somehow the uniform distribution on an LPN ball in terms of what is known as a p-generalized Gaussian distribution. And the advantage is that while you have dependent coordinates, obviously, if you pick a point at random on an LPN ball, you can somehow go to a setting where you have independent coordinates, and these independent coordinates are the p Gaussian random variables. Yeah. So we say that a random variable is p-generalized Gaussian, or has a p-generalized Gaussian distribution, or is p-Gaussian, let's say, if it has a density of this form here. Yeah? So fp of x is equal to e to the minus x to the p over p, and then you get some normalizing constant. It's not important. Yeah? And then Shechtman and Zinn and Rashev and Rüschendorf independently proved the following, that if p is between 1 and infinity, and you have a point uniformly distributed on the LPN ball, yeah, then your point is equal in distribution to the following, to u to the 1 over n, y divided by the p norm of y, and u is uniformly distributed on the interval 0, 1, it is independent of y, and y is a vector having independent coordinates, and those coordinates are p-generalized Gaussians. Okay, so you can go from dependent coordinates somehow to a vector which has independent ones, and this somehow facilitates the computations when you want to prove a large deviation principle somehow related to LPN balls, or the geometry of LPN balls. Okay, so I want to motivate the computations that will follow in a moment by a central limit theorem, because yesterday I said it is somehow a natural question that if you have a CLT, then you can ask, okay, what about the asymptotic probabilities on a large deviation scale, not on a normal scale. So, and let's have a look. So there's a central limit theorem by Schmuckenschläger, who proved this in 2001, which says that if p is between 1 and infinity, q different from p, and q between 1 and infinity, and you have a point which is uniformly distributed on BPN, then essentially the q norm, or the normalized q norm of this vector satisfies the central limit theorem. Okay, so you have convergence and distribution to some Gaussian random variable. This is just the qth, or this is just the qth moment of a p-generalized Gaussian. So this is a central limit theorem that we have. And now we can ask the question, what about a large deviation counterpart to this CRT? Okay, and this is what we're going to prove today. So let's start. So we look at the following quantity. Look at the quantity n to the 1 over p minus 1 over q. Set and the q norm where z is uniformly distributed on the LPN ball. Okay, and we want to prove a large deviation principle here, and we will have to distinguish two cases. Either q is less than p or q is larger than p, and we will get different results depending on the relative position of q to p. Yeah? And yes, because Zahar had so nice pictures, I also made a picture. Yeah, so we now put everything that we had so far in our toolbox. Yeah, so this is principle 1. You remember you have a vector which has independent coordinates, then you get a rate function which is the sum of the rate functions. Principle 1, we're going to use the contraction principle, principle 2, and we're going to use exponential equivalence. Principle 3, we're going to use, what else? We're going to use the Shechtman-Zinn probabilistic representation. What else? We're going to use Cramer, yeah. Cramer's theorem in L2 in R2, yeah. And well, we use a version of Cramer, which I did not present. I'll just mention it in the proof. Version of Cramer for stretched exponentials, yeah. For random variables with stretched exponential tails. I presented already a version, but this is a more general one, yeah, which can be found in a paper by Nina Gantert and Franz Rembert and Kavita Ramanan, for instance, yeah. Okay, so this is the results we're going to use now, and we start with the following case. So the case Q is less than P. Okay, Q is less than P. So first we note that n to the 1 over P minus 1 over Q, this is the quantity we're interested in. That's the quantity we're interested in, is in distribution equal to n to the 1 over P minus 1 over Q, u to the 1 over n, y in the Q norm, and y in the P norm. And remember, this was our vector of P generalized Gaussian entries. Okay, so it has independent P Gaussian entries. Okay, so this follows from the Shechtman-Zinn probabilistic representation, and now we define two sequences of random quantities, namely Wn will be n to the 1 over P, 1 over Q, y in the Q norm, y in the P norm, and another one, Sn, and this will be 1 over n, sum I from 1 to n, yi, mod yi to the power Q, and mod yi to the power P. Okay. So we want to prove a large deviation principle. I said we're going to use Cramer, so let's look at the log moment generating function. So we have what? Direct computation shows that lambda, let's say lambda pq, x and y, this is equal to the log of, well, we get here some normalizing constant, integral 0 to infinity, e to the.
Sorry?
Yeah.
What does it mean, the parentheses in the sum of where you wrote Sn and then you wrote a parenthesis between yq and yp?
I have the vectors. There's a vector containing these with the coordinates yi to the power q, yi to the power p.
Okay, thank you very much.
Yes. So you have x t to the power q plus, and then y minus 1 over p t to the p dt. Right? And since q is less than p, we know that lambda pq is finite on r minus infinity 1 over p. And if you remember what I said yesterday, I said, okay, we have Cramer, it's valid also in higher dimensions, and in particular, we do not need finite exponential moments everywhere. It's enough to have it in a neighborhood containing 0. Okay, and this is the case because this neighborhood contains 0. Yeah, so I can apply Cramer's theorem. Yeah, and remember, Cramer's theorem tells us then that we get an LDP, and the rate function is the Legendre transform. Yeah, so Cramer. So now we apply this tool. So in R2, right? So we get that Sn, n and n satisfies an LDP at speed n. This is what Crameri gives us, with a good rate function, so a rate function with compact level sets, given by the Legendre transform. Yeah, so this is the rate function. Okay, so if I look here, so this is my Sn, and this is the quantity that we're interested in somehow, yeah? or here, yeah, up to this uniform distribution. Yeah? So what I want to do now is I want to contract this thing here, or this thing here, from Sn via a continuous function, and this is as follows. So now we use principle 2, which was I write it again, the contraction principle, with the following function: f 0 infinity to r, and xy maps to x to the 1 over q. This is what you do with the first coordinate, and the second, and you divide by y to the 1 over p. So you get the p norm, right, of the second coordinate, yeah, of the vector y. Yeah, and so we have the following now. We now know that Wn is just f of Sn. Yeah? And because this is a continuous mapping, I have an LDP for Sn. Yeah? So I transform it onto my other space. So I get an LDP for Wn. Yeah? So this satisfies an LDP at speed n with good rate function. Remember, we had this infimum there in the contraction principle. So the good rate function is, let me call it IW of Z, is, well, the infimum over all x positive y, and such that x to the 1 over q, y to the minus 1 over p, this is equal to Z. And this is the rate function we obtained from Crameri. This holds if Z is non-negative, and if Z is less than 0, then this is just plus infinity. Okay. So we now have an LDP for, let me go back, for this quantity. Okay. We want an LDP for the quantity where we multiply with u to the 1 over n. Okay, so we're essentially almost there. So what one can check now, maybe this is a good exercise. One can check the following, that u to the 1 over n and n satisfies an LDP at speed n, and with the following good rate function. The good rate function is IU, let me call it IU of Z, and this is minus log Z if Z is in 0, 1, and it's plus infinity otherwise. Okay. So now we have our separate building blocks. Okay, so we have an LDP for this, or let me do it here. We have an LDP for this. We have an LDP for this. Both LDPs occur at the same speed, namely n. Right. This is what we know so far. Okay. So what we're going to do is just use again. Well, we use two principles now. So first, because we have independence, remember, u and y are independent. So I can use principle one, principle one, because u is independent from y. We know that the vector with the coordinates consisting of u to the 1 over n and wn, those are independent. Yeah? And this sequence satisfies an LDP because this sequence does and this sequence does, and they're independent. This is principle one. So this satisfies an LDP in R2 at the same speed. The speed was n, so at speed n, with good rate function given by the sum. Yeah, so IV of x comma y is what? This is the rate function we get from the uniform or from the normalized uniform distribution, plus the one we get for W. Okay, so now I have the LDP for this quantity. And what I want the LDP for u to the 1 over n times Wn. So I'll just use again the contraction principle. So principle two, contraction principle. We use the function mapping x, y onto x times y, and so we get that f tilde of Vn, which, well, this is equal in distribution to the quantity we're interested in. This is where we started, and I just rewrote it as the product u to the 1 over n times Wn. So this satisfies an LDP at, well, the same speed. So everything has the same speed at speed n with good rate function. Well, with good rate function, I'll write it here. Let's say j of z is the infimum over all x, y non-negative, z equal x times y, and the rate function we got for v, x, y, which was the sum of the rate functions. This we get if z is non-negative, and we get plus infinity otherwise. Okay, so this is the case where q is less than p, and this was so q is less than p. Then we saw that we have lots of LDPs which form our building blocks. We have an LDP for this, we have an LDP for this thing here, and so on. And then from all the principles that I've presented, we build our LDP for the quantity we're interested in somehow. And this worked nicely because q is less than p, and therefore we have finite exponential moments. So we, at least in the neighborhood of 0, so we could apply Cromere. Things change now and get more delicate if q is larger than p, because we lose the exponential moments. So we cannot apply Cromere, or just the Cromere that I've presented, any longer. So let's look at the other case. Because so far we have used several principles, but not everything. So the case q is larger than p. This is the maybe more interesting case. Okay. So for instance, we have not used principle 3 yet. We're going to use it now in this case. So we're going to use exponential equivalence. Okay. So this, as I said, this is more delicate. Because we have no finite exponential moments. So So I want to consider my sequence of p generalized Gaussians independent. Okay, so p Gaussians independent, yeah, independent, and Sn is 1 over n sum I from 1 to n yi to the power q. Yeah? So we will see that essentially, this quantity determines the whole LDP. Yeah? Remember, I mean, what we're actually looking at is this, right? And what I'm saying is that essentially this gives us the LDP if q is larger than p. And the reason will become clear in a moment, and it has to do with the speeds of the LDPs. Yeah, because here we had these building blocks, speed n. This thing here had speed n, and now in the setting where q is larger than p, this thing here has a different speed. It's slower, and these things here, so this thing and this thing here, they satisfy large deviation principles, but at a faster speed. So they rush away, and the only thing we see in the end is this, okay? Because this occurs at a slower speed. So this is the general, this is what's going on behind the scenes somehow, yeah? So we use the following lemma, yeah, which, as I said before, this is a version of Cramer stretched exponential tails, okay? And this can be found in a paper by Gantert, Rembert, and Ramanan, I think 2014 or 15. And this is as follows. So let's say x, x1, x2, and so on are independent. Well, they're IID, okay. IID with the following tail behavior. So we have stretched exponential tails. C1 of t, e to the minus b of t, t to the r, is essentially the tail of x. This is bounded above by some c2 of t, e to the minus b of t, t to the r, and t should be large enough, okay, larger than some t naught, and c1, c2, and b are nice functions, okay, nice functions. They should not, I mean, they're slowly varying functions at infinity, but let's say nice functions, okay. That's enough for now. Yeah. So if this is satisfied somehow, yeah, if we have this tail behavior, which before, you remember yesterday, it was just this, and this did not depend on t. Yeah, I had these constants, and I presented this Cramer for stretched for random variables with heavy tails, and now you can allow instead of constants, you can allow functions here, but they should behave nicely. Yeah. Okay, so if this is the case, if you have such a tail behavior and nice functions, then it follows that 1 over n sum xi I from 1 to n, that this satisfies a large deviation principle at speed. At speed, oh, well, r should be between, I didn't say so, r and 0, 1, yeah, at speed b of n, n to the r, yeah? So this is slower than what Cramer gives us, yeah? With the following good rate function, I of z is what? This is z minus the expectation to the power r, if z is larger than the expectation and plus infinity otherwise. Yeah, so again, we get this non-convex rate function, but we get something, okay? So we get something. We get some rate, and we get a speed different from Cromere, what we had in the case q less than p. Okay. So one can show that we have the following, that we have some indeed nice functions that show the following, that the tail of the qth moment of a p generalized Gaussian behaves like this. So I don't want to write it down explicitly, but what's interesting is just this part here. Remember, we're in the case that q is larger than p. So this is our r. So we get this, somehow this this behavior here. So we have these, remember here, so this were the tails here, okay? And essentially r is then this p over q. And one can show that b of z tends to 1 over p as z tends to infinity. If you do the computations, but I don't want to go into details here, but what I'm saying is our random variables, which do not have finite exponential moments, they still satisfy this condition with nice functions. So what we get an LDP for Sn, sort of LDP. So we get from the lemma. From the lemma, we get that Sn, and an n satisfies an LDP in R at speed n to the p over q. So it's slower with good rate function is, let's say, looking as follows: 1 over p. I absorb this b of z, because if z tends to infinity, this tends to 1 over p in the rate function. Z minus the qth moment of a p generalized Gaussian to the power p over q. Z is larger than mp of q. So this is the qth moment, the qth moment of a p generalized Gaussian. And plus infinity otherwise. Plus infinity otherwise. Okay. So we have sort of an LDP for Sn. And remember, Sn is this. So what I'm interested in, because the quantity we're interested in is the which appears in the numerator, is the q norm of y. So I now just contract the whole thing with the function x maps to x to the 1 over q, and I get an LDP for the q norm. I get an LDP for the q norm. So for this thing here, with normalization. Okay, so now I use again the contraction principle. So principle 2 with the function f x maps to x to the 1 over q, and then we get, and so f of Sn, which is just 1 over n sum I from 1 to n, yi power q, the 1 over q, and an n. This satisfies an LDP at speed n to the p over q, n to the p over q, with good rate function given by j of z being 1 over p z to the q. We contracted here. You can compute this explicitly now, to the power p over q. z is larger than mp of q to the 1 over q, and it's plus infinity otherwise. Yeah? Yeah. So essentially, you have a rate of the form z to the pth power. Okay. And if you're familiar with the results of Shechtman and Zinn, this is essentially what they get. They study somehow the deviations of the quantity we're looking at, and they get some constant, and they get z to the power p. Yeah, and by proving a large deviation principle, we can determine in an asymptotic. So we get an asymptotic result. So it does not imply Shechtman-Zinn, and neither does their result imply this one. But you get precise constants. Yeah, you get the precise behavior. Yeah, because you do not look at constants or absolute constants such that for all n, no, we get some asymptotic result. But the advantage is we discover what the real or the right constants are in this large deviation principle. Okay, so this was just the LDP for the Q norm, or for the normalized Q norm of y. Yeah? So, but we're interested in, I'll write it again. So we are interested in the following. We're interested in this quantity, which we know is equal in distribution to n to the 1 over p minus 1 over q, u to the 1 over n, q norm of y, and the p norm. Yeah? Okay. So if we, so here, let's take some color. So we know that, let me write it the other way around. It's not such a mess. So u to the 1 over n, and to the 1 over p minus 1 over q. So so this here, this satisfies an LDP. Yeah? LDP at speed n, which is much larger than n to the p over q, because q is larger than p. This is also the case for, let me write it like this, for this thing here. Okay, this also satisfies a large deviation principle with a certain rate function, also at speed n. But this thing here, as we have just seen, this satisfies an LDP at speed n to the p over q. Yeah, and this is, I'll write it again here, much less than n. So this is much slower. So heuristically, already now that you've seen this is what you're going to see, because this is slower. Yeah? The rest somehow you do not see the rest because it's too fast. Yeah. So essentially, the largest exponent wins principle. Yeah. And this is the one, the largest exponent. Yeah. It's e to the minus n to the p over q. This is what you see. Okay. So this is just the heuristic argument by comparing the speeds of the LDPs, of the separate LDPs. And to formalize the whole thing, you prove that this thing here, the whole thing, for which you want the LDP, is exponentially equivalent to, well, this is not good here. It should be like this, right? That this expression here we're interested in is exponentially equivalent to this expression here. And because we have established the LDP for this expression here at the speed n to the p over q with a certain rate function, non-convex, then we get, because of exponential equivalence, this is principle 3, as I explained, if you have sequences of random variables which are very close, I mean close on an exponential scale, then they satisfy the same large deviation principle. So in order to formalize this comparison of speed argument, you show that this is exponentially equivalent to the whole thing. Yeah. And then the whole thing, which means this, satisfies the same large deviation principle. Okay, let's at least somehow sketch this argument. I mean, how much time do I have? Okay, so I can really just sketch it now. So let delta be positive and say epsilon is in 0, 1. Yeah. So then this goes as follows. You look at the probability. Yeah, we want to show that this is exponentially close. So we look at this quantity. This is the quantity we established the LDP for using this stretched exponential Cramer. And we want to compare it with the quantity we started with, which is this. I'm just rewriting it. Yi to the power q to the 1 over q, and here we get the p norm. So 1 over n, I from 1 to n, yi to the power p to the power 1 over p, and the probability that this is larger than delta. And we want to show somehow that that the whole thing tends to minus infinity, right? If I look at the log and I normalize with the speed and to the p over q, then the lim sup of this goes to minus infinity, which means that these two quantities are close on an exponential scale. Yeah? So because time is almost up, I'll skip the details here. But what you get is the following: you get five terms, of which the first one. So you just separate everything here. Yeah, you just separate everything. You take out this part here, and then split your probability in different parts. What you get is the part that you already studied, namely the Q norm, or the normalized Q norm, and the probability that this is larger than delta divided by epsilon, plus lots of other terms. Yeah? The probability that u to the 1 over n is less than root 1 minus epsilon, plus the probability that 1 over n, then you get this part to the power p, that this is larger than 1 minus epsilon to the power minus p over 2. As I said, I skip details here. Then you get another part, 1 over n, larger than root 1 plus epsilon, plus some other term, which is of the form as above, but less than 1 plus epsilon to the power minus p over 2. Okay. And the thing now is, this here, so all these parts decay at speed n. Yeah, so it's e to the minus n by Cramer. Yeah, by Cramer. Yeah, because you remember we proved the large deviation principle for this. The large deviation principle for this follows by Cramer because this has the exponential moments. Yeah, this doesn't. Yeah, so we proved an LDP for this. We know LDPs for all these terms, essentially. So you know that those terms here, they all decay much faster than this one. Yeah, and so by the largest exponent wins principle, this is the only thing you see in the end. Yeah, so what you get then? So. How much time left? Well, okay. So what you get then, if you continue, the whole thing is then less than something, minus 1 over p, delta over epsilon to the power q minus mp of q to the power p over q, if delta divided by epsilon is larger than mpq to the 1 over q, and it's minus infinity otherwise. And as you remember, you want to show that the whole thing tends to minus infinity. And if epsilon tends to 0, epsilon was arbitrary, then you get the desired bound by minus infinity. Okay, so letting epsilon tend to 0, we obtain exponential equivalence. Exponential equivalence. So principle 3 tells us that n to the 1 over p minus 1 over q set in the q norm and an n satisfies an LDP in R at a slower speed, n to the p over q, with good rate function j. You remember j? So j is the same as before. This was the one we got for the normalized q norm. Okay. So yeah, so let me stop here. So you've seen all the principles and actions. So the general. So this is principle 3. So this is one way to prove, or one way. This is a way to prove large deviation principles. You somehow dissect everything into building blocks for which you can prove large deviation principles somehow, and then you use your principles to build everything up from the ground again to get your large deviation principle for the desired quantity. Okay, and you've seen that essentially we used that the uniform distribution on LPN balls has a probabilistic representation which facilitates all the computations. So if you do not have such a probabilistic representation, you run into immediate problems. And tomorrow I'll present a recent paper of Kim, Liao, and Ramanan, where they somehow overcome this difficulty and for instance, manage to prove large deviation principles related to all-edge balls instead of LP balls, okay, where we don't have such a probabilistic representation. Okay, let's